Hello, everyone. I hope that everybody is fine and enjoying the quarantine. So we are going to have this first session on universal transverse Mercator. This is going to be the first video of about probably 3 videos. So I hope you enjoy. In our last lectures, we discussed about transverse Mercator. At that time, I mentioned that the transverse Mercator became a very important projection because from its basic idea, there are several systems that were derived, and by system here I mean essentially the same transverse Mercator with a different set of specifications. The most well-known specification, which is used everywhere, is the universal transverse Mercator that we know by simply calling it UTM. So it is a system. It comes from transverse Mercator, and here I'm already telling you that transverse Mercator has different names, and here in this slide I'm referring to as conformal projection of Gauss. And it provides, of course, a representation on a plane of the terrestrial ellipsoid, and there are a set of specifications. These specifications were suggested by a French geodesist called Pierre Tardy. The whole idea was that the International Union of Geodesy and Geophysics was looking for a common projection to be used in the mapping of Africa. So in this big scientific meeting in 1936, they accepted the what is known today as UTM. It can be also called the Gauss-Tardy system, which we use today. Whenever I talk about UTM, I like to present it as a development over time. We had the opportunity to talk about Mercator projection, whose basic idea is that of a cylinder normal to the Earth, in the sense that the axis of the cylinder coincides with the rotation axis of the Earth. The cylinder being tangent to the Earth along the equator, it is represented as a straight line and called the standard parallel. All meridians and parallels are represented as straight lines. The characteristics of the transverse Mercator, as presented by Johann Heinrich Lambert in 1772, are: the cylinder is transverse, the cylinder is tangent to the Earth along a meridian, which is called the standard meridian. The standard meridian is represented as a straight line in the projection, and all other meridians are projected as curved lines facing the standard meridian. The equator is represented as a straight line, and all other parallels are represented as curved lines curved towards the poles. Mercator is popular for navigation because loxodromes are represented as straight lines. Its big disadvantage, though, is that the linear distortions are very large. For example, at a latitude of 60 degrees, the coefficient of distortion k equals to 2, meaning a distance on the ellipsoid doubles its length on the Mercator mapping plane. Transverse Mercator is much better than Mercator. As example, I have evaluated the coefficient of distortion for a point distant 60 degrees to the standard meridian using a mid-latitude. Coefficient of distortion k equals to 1.27 is still a large distortion, but much less than Mercator's. In order to have the smallest coefficient of distortion possible, transverse Mercator started to be used under certain specifications. It all started with Gauss. Johann Carl Friedrich Gauss, who I usually call an old Brunswicker since he was born in Brunswick, Germany in 1777. He died in 1855 in Hanover. Gauss was a German mathematician and physicist who made significant contributions to the many fields in mathematics and science, sometimes referred to as the greatest mathematician since antiquity, or even as the Prince of Mathematics. In 1818, Gauss shocked his colleagues by accepting a commission to carry out a geodetic survey of the Kingdom of Hanover, a job which many regarded as beneath his intellectual stature. For more than a decade, he traveled across the country on horseback during the summer with a surveying crew. He used his experience to develop a heliotrope, an instrument that reflects the sun's rays in a focus beam that can be observed from several miles away, and to discover of a way of formulating the concept of the curvature of a surface. For the representation of his work, Gauss used the transverse Mercator. He did not publish his formulation and computations, which were found later in correspondence he kept with friends. In 1912, German geodesist Johann Heinrich Louis Krüger gave form to the theory of Gauss projection, which allowed it to be used in many countries. That is why Gauss projection is also known as Gauss-Krüger projection. In essence, it divided the Earth into zones in order to reduce the linear distortion. There are different implementations of the Gauss-Krüger projection. Later, French geodesist Pierre Tardy suggested the specifications for the system we know as UTM. UTM has the following specifications. It's a projection based on Gauss using a transverse cylinder and secant. The cylinder is secant, not tangent. The Earth is divided into zones with amplitude equals to 6 degrees, coinciding with the zones of the digital chart of the world, which is in the scale of 1 to 1 million. The system is limited in its use to latitude up to 80 degrees. The origin of the coordinate system within each zone is at the crossing of the equator with the central meridian. The scale reduction factor, which corresponds to the scale factor at the central meridian, is called K sub 0 or K0 or kappa 0, and it's equal to 0.9996. And the zones, a total of 60, they are numbered, and they start the number at the antimeridian of Greenwich, increasing to the east. This diagram shows the zones and the zones numbering. Looking at the lower part of the slide, we can see that the first zone starts at a meridian of longitude equals to 180 degrees, and then it increases as we move eastward. So the second zone will be limited by the meridians 174 degrees west, 168 degrees west, so on and so forth, until the zone number 30 reaches Greenwich. We can see lambda equals to 0. But the interesting thing is that Greenwich is not a central meridian. Greenwich is a meridian that divides zone 30 to zone 31. And the numbering continues until arriving at zone number 60, whose limit is at the meridian of 180 degrees. The other thing is, how can we compute the longitude of the central meridian? The longitude of the central meridian is always going to be a multiple of 6 degrees plus 3 degrees. So, which means that we can start with n, and n here is just a count number. Can be 1, 2, 3, etc. And it's always going to give the longitude of the central meridian. The zone numbering is very important, but it's interesting to mention that in most part of the world, uh, people use the longitude of the central meridian to identify the zone. Now, this slide shows a map that has been actually downloaded from Natural Resources Canada, which shows the division, this distribution of the zones along Canada. We can see that the first zone that covers Canada is zone number 7, which gets a little bit of the, well, it gets the whole border between Alaska and Yukon. Then we have the second zone, which is zone number 6, which covers Yukon and a bit of the Alaska Panhandle. Zone number 9, which gets the northern part of Vancouver Island. Then we have zone number 10, which gets Vancouver Island, and so on and so forth, until we go all the way to the very last zone, which is zone 22. Zone 22, actually, it covers the Avalon Peninsula in Labrador. So we can see that Canada, because of its huge east-west extension, it's covered by many different zones. Now, everything would be perfect if not for a few problems. There are certain regions or provinces, for example, here New Brunswick, which is contained in 2 different zones. So we have the eastern part in one zone and the western part in another zone. So that's not really kind of a convenient for mapping of the whole province. We have another problem that Toronto here is also, the Great Toronto area is also covered by 2 zones. So that's why certain municipalities, they have developed a slight modification, the UTM, that some people call the modified UTM, and they're going to see, but they're very specific, and only certain locations do that. On the other hand, you can see here that Nova Scotia is blessed because it's basically all of it contained on the same zone. One of the biggest and most important characteristics of UTM is the use of a cylinder that is second to the ellipsoid. So this figure shows the consequence of that. The cylinder, it pierces the ellipsoid along 2 lines, and these 2 lines are known as lines of no distortion, because the coefficient of distortion along these 2 lines, they're equal to 0. It's important to realize that they're not meridians, but they're just lines which are essentially parallel to the central meridian. The central meridian is going to be represented as a straight line, the lines of no distortion will be represented as a straight line, and the equator will be represented as a straight line. What is the advantage of using a cylinder that is second instead of a tangent? We will be decreasing the linear distortions. So the cylinder is perpendicular in the sense of its axis is transversal to the rotation axis of the Earth, and it's second, and it's going to be second at each partial system zone. So in essence, we are talking here about 60 second cylinders. Throughout the second lines, there will be no scale distortion. These are the lines of no distortion, k equals to 1. There will always be reduction of scale within the area between the second lines, and there will always be increase in scale in the area between the second line and the limit of a zone. The biggest reduction in scale throughout the central meridian of a zone is going to be equals to 0.9996. This is very important, and that's something that you essentially have to memorize. You memorize that by it will come in the blood. Anyway, the biggest amplification in scale happens along the limit of the zone at the equator, where the coefficient of deformation equals to 1.001. Let's reinforce the idea of one of the consequences of using a second cylinder, which is the creation of a region where there is reduction in scale, which means the coefficient of distortion will be less than 1, and there's going to be a region of increase of scale, which means basically that the coefficient of distortion is greater than 1. As there is no one to choose a color for me, let me use red. So here we have the central meridian. Okay, here we have the line of no distortion, one here and the other side, and here we have the indication of the meridians that are the limit of a particular zone. So what we have in here is the scale factor. This is the ratio between the distance on the mapping plane and the distance on the ellipsoid. So the curved line here that we can see is basically the ellipsoid, and the plane is the mapping plane. Here it is, the mapping plane. Okay, so what we have here is a distance on the ellipsoid and the corresponding distance, the projected distance on the mapping plane. So if I apply the ratio, we are going to see that the value of k is going to be less than 1. So the distance on the ellipsoid is larger than its corresponding projected distance on the mapping plane. At the line of no distortion, of course, both distances are the same, which means that the coefficient is going to be equal to 1. And if we go now to the region between the line of no distortion and the limit of the zone, we are going to see that the coefficient of deformation now is going to be greater than 1. Okay, so that's a very important characteristic of the UTM system. The use of a second cylinder implies reduction in scale. This concept can be seen geometrically. Let us consider the red ellipsoid in the center, and it's touched by a cylinder along a particular meridian, as the case of the transverse Mercator. The coefficient of deformation k can be seen as the radius. A second cylinder implies that it is also tangent to a smaller ellipsoid, represented here in blue. Therefore, all features are smaller. It is, the original scale was reduced. The radius of this blue ellipsoid is k sub 0. In practice, all linear expressions from the transverse Mercator will be multiplied by this coefficient of scale reduction k sub 0. The consequence of this reduction in scale is that all linear distortions will also decrease. Now let us talk about coordinates. The original map projection, Gauss decided to call the coordinate axes x and y the ordinate, and x the abscissa. In the UTM systems, the plane rectangular coordinates are usually designated by the letters N and E, replacing x and y. N means towards north or northing, and E represents towards E or easting. And both should precede the values of the ordinate and the abscissa, respectively. Attention should be paid because it is still customary to find UTM coordinates to be referred as x and y. The UTM system uses the concept of false coordinates. The origin of the coordinate system in each zone is the intersection of the central meridian and the equator, both represented as straight lines. There are constants added to the origin. So for north, the constant is 10 million meters, and for easting, the constant is 500,000 meters. The interesting thing is that if you go from the equator towards the north, you start from 0. So as a matter of fact, the origin has different numerical values as far as northing is concerned. So, which means that the value of the coordinate n is going to be 10 million minus n prime, and n prime here is the distance from the equator to the point. And for the northern hemisphere, the value is going to be n equals to n prime. Again, n prime is the distance from the equator to the point. For easting, it's going to be 500,000 plus or minus e prime, and the z prime represents the distance between the central meridian and the point of interest. Consider now these 2 points located east or west to the central meridian and north or south with respect to the equator. The coordinate n, or northing, of the point in the southern hemisphere is equal to the constant at the origin, 10 million meters, minus the distance between the equator and the point n prime. The coordinate n, northing, of the point in the northern hemisphere is equal to the distance between the equator and the point n prime. The coordinate e, easting, of the point west to the central meridian is equal to the constant at the origin, 500,000 meters, minus the distance between the central meridian and the point e prime. The coordinate e, easting, of the point east to the central meridian is equal to the constant at the origin, 500,000 meters, plus the distance between the central meridian and the point e prime. All that is the same as if we considered the origin with values 0 located outside the zone as indicated in the red. Let's go back to linear deformations and let's see what happens when we introduce a second cylinder. We have in this slide the equation, the definition of scale factor, the ratio between the distance on the mapping plane and the distance on the reference ellipsoid. Around a particular point, the scale factor is constant. That's a characteristic of conformal mappings. For a tangent cylinder, the scale factor we are going to call here K prime is the scale factor of a tangent cylinder. It corresponds to 1 plus E prime square over 2R square. This is an equation that allows us to compute an approximate value for the scale factor as a function of the easting coordinates. If we are going to introduce the coefficient of scale reduction, what we're going to do is basically multiply, and we get a color here, we're going to multiply the scale factor of the transverse Mercator by the coefficient of scale reduction, K sub 0. Okay, and here we have K sub 0 multiplying K prime. This K prime is the one that we defined before. In the central meridian, it is whenever E prime equals to 0, of course, E prime is going to be equal to 0. Therefore, the equation reduces to K equals to K naught, to K0. Okay? And now just a comment. The evaluation of this E prime here is given by this expression here. Okay? As we mentioned before, the introduction of the second cylinder results in a zone, or let me call it an area to avoid confusion, area of reduction of scale and area of amplification of scale. And the maximum value of the scale factor is going to be at the limit, the very limit of the zone, and the smallest scale factor is going to be at the central meridian. Here we have a diagram, and we have to think of these at the equator. That's a interesting way of looking at it. We're going to have a different diagram in the next slide. We have the line in the center represents the central meridian. The easting equals to 500,000. The scale factor equals to the coefficient of scale reduction, 0.9996. Then we have to the left and to the right the lines of no distortion. That's where the second C takes place. They have easting of 330,000 meters to the west and 680,000 meters to the east of the central meridian. And of course, the scale factor equals to 1. And finally, the maximum scale factor we have is for points at the equator, the intersection of the limit, the limiting meridian of the zones. They have easting of 166,000 meters to the west of the central meridian, and easting of 834,000 meters to the 166,000 meters to the west of the central meridian, and 834,000 meters to the east of the central meridian. And at these points, the scale factor equals to 1.0 0.001. A different look at it is if you're looking at the projection on the mapping plane. We have the central meridian represented as straight line. We have the lines of no distortion. The second lines represented also as straight lines. Perpendicular to them, we have the equator. And the two curves here represent the projected meridian. Okay, these are the limits of the zone. Along the central meridian, the scale factor equals to 0.996. Along the second lines, the scale factor equals to 1. And at the very last end of the along the meridians intercepting the equator, we have the largest scale amplification, okay, which is 1 plus 1 over 1025, which is essentially 1.001. Here we have the distances and the angles. So in terms of distance, the distance between the central meridian and the second lines equals to 180 kilometers. It's a constant value, or 1 degree and 37 minutes. The distance from the central meridian to the very end of the zones along the equator is 334 kilometers, and we can see it decreases until 0 at the poles. In angular terms, it corresponds to 3 degrees. The linear deformation can be computed very accurately with the equation that is presented. In this equation, we have the k sub 0, the constant. We have this term 18 in Roman numbers, which corresponds to 10 to the power of 12 divided by 2 times r square k0 square, and r square r here means the radius of curvature following the Gaussian definition. And we have this term q, which is computed as a function of the quantity e prime, which is the distance from the central meridian to the point of interest. So please copy down this equation here, because we're going to have an example the next slide. Okay, consider these 2 points. One point has east or easting coordinate 510,000 meters, the other 520,000 meters. Both are to the east of the central meridian, of course, because they are both greater than 500,000. So we have to compute the term q squared. The q squared is a function of these terms q1 and q2, and they are basically 10 to minus 6 of the difference between 500,000 and e prime. So it corresponds to q1 is 0.01 meters, q2 equals to 0.02 meters, and we can compute now Q prime, which is 1/3 of the summation of Q1 square plus Q2 square plus the product of Q1 and Q2. I'm given here the radius of curvature due to Gauss, and this point, for the latitude of this point, is very close to the equator. Okay. Evaluating the term 18. The term 18 is given there, and then we have all the numbers to compute the scale factor K. So we can see that these 2 points, this is the scale factor for the distance. Okay, so this would be essentially the mean scale factor, which in practice we just call the scale factor, but that scale factor for the distance between these 2 points. And we can see that it's 0.999603, so it is in the area or reduction of scale, which means that the point lies between the central meridian and the line of no distortion. Okay, and I think that here we end this section, and this should be section or session. Interesting. Now I don't know. Anyway, you can tell me if it is section or session. And you can also tell me if section writes with C or with an X. So talk to you later, guys.